Thank you for joining me in today's lesson. In this first tutorial, we will use the difference quotient to find the slope of the tangent line to any curve. We are in the first half of section 13.4 in our textbooks, and we're looking at the tangent line problem from calculus. Let's look at this graph. This might be the graph of a quadratic. It is definitely a continuous curve. We can determine the rate of change, or in other words, the slope of any curve at a single point by finding the slope of its tangent line. What I mean by that is there are infinite slopes along this curve. It just depends on which point we are on the curve. For example, if I talk about this point, and I'll label this as x1, y1, if I were looking for the slope at this one point, what I would need to do is find the slope of the line that's tangent to the curve at that one point. So I'm going to do my best to draw a nice tangent line to this curve. So let's say that that's the tangent line to the curve sharing this one point. If I could find the slope of this tangent line, then that would be the slope of this curve at that point. Let's move to another point. Let's take the point that's right here. I'll call that x2, y2. If I wanted the slope of the curve at this point, then I would need this different tangent line. Let's say that's the tangent line. Again, tangent lines just share a single point. We can see that the slope of this brown tangent line is positive, just like this black tangent line is positive, but it's starting to decrease in terms of slope. This is a steeper slope here than this one. Let's say we took a third point right here at the local maximum. I'll call that x3, y3. If we have a point right at the top of a curve, a turning point, then the tangent line, of course, would be a horizontal line right there. And of course, the slope of a horizontal line is 0. So it looks like as we have points on a curve where we're increasing, that the slopes would be positive, but starting to decrease in terms of steepness until we get to the very top of the curve. Then we have a slope of 0. If I pick one more point, and let's put it on the decreasing part of this curve, and I'll call this x4, y4, the fourth point, the slope of this point, or of the curve at this point, would be the slope of this tangent line, which now is a negative slope. So we can see where we'll, on the curve where we will have positive slopes, we see on the curve where we will have negative slopes, and in between the positives and negatives is that one slope of 0 at the top of our curve. Now I understand we're talking about a tangent line right at this point. Tangent technically means that we're just sharing that one point. If this curve didn't go like this, let's say that it started to curve and turn back up, technically this red line would intersect the curve at another point over here, so it technically would not be a tangent. That's not what we're talking about. We're minimizing the domain such that this is a tangent line just at this single point. It doesn't matter if this line all the way down here is going to go through the curve somewhere else. So we have positive slopes until we get to our 0, and then we have negative slopes on our decreasing part of the curve until we get down here to maybe a fifth point where we would have yet another turning point, a slope of 0, and then we'd go back to having positive slopes up this increasing part of the curve. So that's what we're going to be doing today, finding the slope at tangent lines to the curve. Let's go a little bit deeper. Let's say we have this part of a curve and see if we can calculate the slope. So let's pick a point on this curve. I'll just pick this point right here, and I'll call this ordered pair x, and then I'll call the y-coordinate f of x. since that's what a y-coordinate is. Whatever x is, f of x would be the point on the curve. I'd like to find the slope of the tangent line through this point. Before I do that, let's pick another point, and I'm just going to arbitrarily pick it over here. Now we've gone a little bit of distance in the x direction. So when I name this ordered pair, what I'm going to do is I'm going to call it x plus some horizontal change. So that's why I'm just going to use x plus h. So I don't know what h is. It's just over here somewhere. This point has that as the x-coordinate, so its y-coordinate would be f of whatever x plus h is. So that ordered pair is right here. If I connect these two points with some sort of dotted line, hopefully a nice straight line, obviously, this dotted line is not the tangent line at this point. But let's start with this. We know how to find the slope of any line given the 2 points. So I'm going to come over here and talk about the slope formula. The slope formula, which we label as little m, is delta y divided by delta x, meaning the change in the y's divided by the change in the x's. So our slope is going to be, we're going to take the y-coordinates and subtract them. So here's one y-coordinate and here's the other y-coordinate. Let's subtract bigger minus smaller. So f of x plus h, this first y-coordinate, minus subtracting this y-coordinate, f of x. Underneath, in the denominator of our slope formula, is the change in x. So I'm going to take the x-coordinate and subtract the other x-coordinate, of course in the same order. So I will take the x plus h and subtract the other x-coordinate, which is just x. Let's simplify this fraction. The numerator is going to stay what it is, f of x plus h minus f of x. The denominator has an x minus an x, so those terms cancel out and we have h. We've seen this before. This is called our difference quotient. Our difference quotient represents slope. So this is how we can calculate slope given this picture. Unfortunately, this dotted line is not the tangent line because we added too big of an h. Let's say we picked this point right here. That's a little bit, if I connected these 2 points, we still don't have the tangent line, but it's a little bit closer to being the tangent line. H is not as long, or I guess as big as this h, it's a little bit closer. Let's pick another point that's even closer. Let's say this fuchsia point right here. And we connected these 2 points. We're getting a little bit closer to the tangent line. Again, it's still not the tangent line because we still have, a bit of an h in here. So we are connecting through, we're going through the curve and then back out. Ultimately, we want h to be as tiny as possible. In fact, wouldn't we just love if h is 0? If h were 0, then I would have the tangent line. Unfortunately, that's the one number that h cannot be because we cannot plug 0 into this fraction, into this difference quotient, which is why we are going to take the limit as h approaches 0 of this difference quotient. Remember, when we're taking limits, it doesn't matter what happens at 0, it matters what's happening on our way to getting to 0. And that is exactly what we're going to be doing today, and that is the true meaning behind the difference quotient. Okay, so the difference quotient represents slope, and the limit as h approaches 0 of the difference quotient represents, as h is tinier and tinier and tinier, this will now represent the slope of our tangent line at any single point on our curve. So this is how we will calculate the slope of a tangent line. Let's look at our first example. Now I'm starting with a pretty simple example because this actually is just the equation of a line. We all know that the answer to this, if we're looking for slope, the slope of this line at any point really is -3. I wanted to start with something that you knew was true, so that you can see that the math is going to prove that our slope is -3. So we want to find the slope of g of x at any point. What we're going to do is use our difference quotient to find the slope. So slope is our little m, and we know that that's going to be the limit as h approaches 0 of our difference quotient. In this case, we're using g of x, so it's going to be g of x plus h minus g of x over h. So our difference quotient is always the same thing, except sometimes it's an f, sometimes it's a g, sometimes it's a j or a k. It just depends on which function we're given. So we need to calculate g of x plus h. That's the first part. So we're going to basically be plugging excuse me, let me change color. We're going to be plugging in an x plus h, substituting that into this function. So let's write, first of all, we can't plug in, I'd love to be able to plug in a 0 right now. I can't do that. If I plug in a 0, I get a 0 in the denominator. If I plug a 0 in for h here, I would have g of x minus g of x, which again would be 0 divided by 0. That's good news because there's that common factor that we're going to be able to cancel away. And that common factor is the h that we see right here. So until we can cancel out that common factor, I'm going to continue to write my limit symbol. I'll put the h in the denominator. So g of x plus h, I take g of x and I replace this quantity, this input, with an x plus h. So it's -3x plus h plus 4. That's this part. I'll change color. Color coding might be good. Minus g of x, so that's what comes next. So I'm just going to put the g of x function here. Of course, this should always be put in parentheses, especially if there are multiple terms. I'm subtracting this part, which happens to be a whole binomial. So that's our first setup. Now I'm going to distribute here, and I'm going to distribute here and see what happens with my like terms. So here's the limit as h approaches 0, -3x, -3h, +4, +3x, -4. When we do this difference quotient, the terms that come out of this part of the difference quotient will always be the opposites of other terms over here. We see a +3x with a -3x, so therefore they cancel away. We see a -4 with a +4, so they will cancel away. This will always, if you do this correctly, this will always happen. The terms that come out of here, as long as you use your parentheses and distribute, will always be the opposite of terms that are from this part, leaving only things with h's. You should only have terms that have h's in them, and it's a -3h divided by an h. Now I can see that I have that common factor. I can cancel away this common factor, and I'm left with the limit as h approaches 0 of -3. Since there's no more variable, there's really doesn't matter what number I plug in for h, this limit will always be equal to -3, which is why the slope at any point will always be equal to -3. So again, I wanted to go through one problem first where you already knew the answer. So here is the formal definition of proving that the slope of this tangent line will always be equal to -3. Of course, we already knew that because we know Algebra 1. Let's go to a new problem, and now let's look at the slope of a curve. F of x equals x squared. This, of course, is a parabola. There are infinite points on this parabola, and each point has a different tangent line. So therefore, the slope keeps changing. I want to find the slope at this point. So before I think about this point, what I'm going to do is I'm just going to find the slope at any point like I did with the previous problem. So I'm talking about slope, I'm talking about m equals, I'm talking about the limit as h approaches 0 of my difference quotient. It's f of x again. So f of x plus h minus f of x divided by h. So let's plug into this. We're first talking about f of x plus h. The x plus h is going to substitute right in for that input, and I'm going to square it. So I'm going to have the limit. You got to write your limit symbol every step along the way until we can plug in a 0 for h. which we can't do until we cancel that factor out. F of x plus h becomes x plus h quantity squared, because that's what it says to do. Take the thing and square it, minus f of x. Well, f of x is just a little x squared, so there we go. I know this should be in parentheses, but since it's only one term, there's no distribution really. So that's our first plug-in step. Now we'll square this binomial. X squared. The inner terms become an xh. The outer terms become another xh. There are two xh's. Last term, h squared minus x squared. Whoops, x squared. Like I said, this stuff, which in this case it's only one term, will always be the opposite of something from over here. And there it is, I see it. Now, if you have trouble squaring a binomial, you can always come off to the side, x plus h and x plus h, and do your FOIL to see all four terms, the inner and outer terms combined to give me two xh's. So that's where we are. This x squared and this negative x squared cancel away, and you can see that all the terms that remain have an h, which is important because we are trying to cancel that common factor. And in fact, what I'm going to do with the two terms that have the h, I'm going to pull the h out, leaving it as a GCF, leaving a 2x plus the other h factor from here. And then I can cancel away that common factor. Finally, I will have an expression 2x plus h, and I can plug 0 into it. When I plug a 0 right in there for that h, I would be left with just 2x. And that's what our slope is. Our slope is equal to 2x. Now obviously this is an expression, and each x value is going to change the value of the slope. So if I'm looking for the slope when x is negative 2, if the slope is 2 times x, then this slope is going to be 2 times negative 2, which would be negative 4. That's my answer. So the slope at negative 2, 4 is equal to negative 4. Let's say I wanted to find the slope at a different point. Let's say the point 3, 9. I know that 3, 9 is on this curve because if I plug in a 3, I get 3 squared as the output, which is 9. If I wanted the slope at this point, then I would plug a 3 into this formula, into this expression for slope, and this slope would be 6 because 2 times 3. What if I wanted it at another point? Let's say I wanted it at the point negative 5, 25. I know that that point is on this curve because negative 5 squared is 25, and I would just need to plug this x coordinate into this expression for slope, and I would have that the slope at this point would be negative 10. So the book, if you go and read this section in the book, they're going to do this problem a little bit differently. If they're looking for the slope at a specific point, they actually don't use f of x plus h and f of x. They plug the negative 2 right here, so f of negative 2 plus h and f of negative 2. And they will do all this work and they will find the answer of negative 4. But then they'd have to do that same work, all of this work again, for a different point here and for another point here. So it would be like 3 times the work. What I suggest that we do is find the slope in general using the value of x along the way, get an expression for slope, and then we can easily just plug in x coordinates 1, 2, 3 and find our 3 separate slopes. I think that that's a more efficient way to do a problem like this. So when we go to example 3, it says find the slope at any point for this curve. Here's our new curve, x squared plus 3, and then use the expression to find the slope at this point and to find the slope at this point. So I'm going to hold off on these points for a bit. I'm going to go and do my difference quotient, my tangent line difference quotient to find the slope of this curve at any point, and then I will plug in a negative 1 and plug in a positive 2. So let's do that. So we have m equals the limit as h approaches 0 This time we have m of x plus h minus m of x all divided by h. Now our difference quotient has m in it because we're talking about m of x. So let's first figure out what m of x plus h is. Obviously we cannot plug in a 0 for h for a while. M of x plus h, we're plugging in x plus h right in here in place of this x. So we're going to square our input. So square the x plus h and then add 3. So there it is. There's m of x plus h squared plus 3. Then we're subtracting the entirety of m of x, which is x squared plus 3. Make sure you do that in parentheses. And that's, of course, still all over h. All right, let's square this binomial. Hopefully you're going to square this binomial plenty of times so that you can just go straight to it. X squared 2xh h squared. Squaring a binomial almost always results in a trinomial. Plus 3, and then minus x squared, and then minus 3. You can distribute that. And like oops, all over h. And like I said, both of these terms, or all of the terms that come out of this, will always be opposites of terms that came before it, leaving only things that have h's in them. So we're very close. We're very close. The only things up in the numerator now, the only two terms share an h, so I can factor that out and be left with 2x plus the other factor of h, and it's all divided by h, and then finally I've canceled out that common factor, leaving the limit as h approaches 0 of 2x plus h. And finally I have an expression that I can plug a 0 in right in there for h, and I get 2x. My slope, once again, is the expression 2x. And I'll explain why it's a 2x again. So now we're looking for two answers. We're looking for the slope at the point -1, 4. And that's as simple as just plugging a -1 right into this expression, and we get -2. And we're also looking for the slope of the point 2, 7. And that's just plugging a 2 into this expression and getting 4. So those are my two slopes that I'm looking for at these two specific points. Thanks for watching this tutorial, and I'll see you in the second one and in class to practice. Why, thank you. Bye-bye.